Hello everyone, and we'd like to welcome you to our Solar Plus Storage proposal for Ball State University. We'd like to thank you to take the time to watch our presentation, and we'd like to get started. So throughout this presentation, we'll start off by introducing ourselves and what we do, and then we'll go into the specifics of the projects, including the components and goals we'd like to reach with this project. We'll go in through the stages of how we'd like to implement our PV and solar system, and we talk about how we'll market it to make sure that our community and stakeholders are on board with what we have. So to start off, I'm team captain. My name is Zahra Amin.
Hi, I'm Sylvia Cressman. I was our financial lead.
I am Andrew Dingle, and I was the Aurora Solar head.
Hi, I'm Grant Homan, and I was the lead for OpenDSS.
I'm Annie Wolosko, and I was the public permit and zoning manager.
And in the audience today, we have our faculty assistant, Dr. Paul Berger, and for the Q&A session, we'll also invite our electronics advisor, Michael Gregg.
So we are Buckeyes Solar. We are a group of engineers and environmentalists who are working to achieve the goals you have for the photovoltaic system. So in our simulations, we used Aurora Solar, OpenDSS, and some case studies to get the optimized results for the implementation of this PV system. Historically, there have been a lot of doubts and skepticism. There has been a lot of doubts and skepticism about solar, but the declining cost of wind and solar and now batteries makes it conceivable to consider 100% renewables, according to Paul Denholm of NREL.
To help optimize our renewable resources, we will be using a solar plus storage system. So we'll use our solar panels to charge our battery. And this will allow for us to peak shave, value stack, and better use our energy that we generate. And this is good because, as NREL stated, when storage is appropriately sized, co-locating and sharing components can increase the net value of a PV plus storage system.
So currently, without our solar system in place, Ball State University emits up to 90 million kilograms of carbon per year, according to the 2017 CIMAP reports. But with our solar system in place, this figure becomes a lot better. With our SunPower solar systems, Ball State University can have up to a 14% energy offset and an additional $5 million profit. Our plan creates a much more sustainable future for Ball State University.
So the major components that we're going to be discussing today include the electronics that we chose, such as our inverters, the panels that we decided to implement, and overall the financial path we decided to take to best optimize our system.
So the panels we decided to go for was SunPower E-Series. These monocrystalline modules have a 20% efficiency, which is one of the highest rated in the market. We wanted to concentrate on efficiency, as a higher efficiency panel would help us convert more electricity, helping Ball State University power the campus. The panels themselves are made off of SunPower Maxion solar cells. These solar cells are different from conventional solar cells as they have a copper backing, which helps with corrosion and makes a longer lifespan for the panels. They also don't have bus bars or grid lines, which gives more surface area that can absorb the sunlight and make a better, more efficient system and panel. We also like to think about other systems besides just the PV system. So one thing we wanted to implement is a way to reduce carbon emissions. We decided to do this by implementing carport systems that have an EV charger, allowing for faculty, staff, and students to make the decision to have an EV car and not have to worry about charging. And it'll reduce carbon emissions and help air pollution at Ball State University. Another thing we like to consider is overall environmental awareness. So our panels, the E-Series panels, are cradle-to-cradle bronze certified, which means they're sustainably sourced and they come from ethical practices. We also use cable management that has 92% recycled rubber. And the cleaning robots we want to implement for our ground mounts and carports use 75% less water than manual methods, saving Ball State University money in the long run and sticks with their goals and aims of sustainability and environmental awareness. So our predictions for this is that we'll have a 14% energy offset for our overall system. This will include 20,000 panels, give or take a few, and multiple string inverters and microinverters. We also hope that the EV chargers will help decrease fuel consumption and air pollution around the campus area, beautifying it while still staying sustainable.
So we designed our system to meet an 85% irradiance minimum, meaning that any areas that received less than 85% direct sunlight would not have any panels. This was done in order to maximize power and save money. Inverters were selected based on conversion efficiency and max power capacity in order to match the output from our panels. The model we created in Aurora Solar consists of a little more than 20,000 panels, consisting of ground mounts, carports, and rooftop mounts. Ground mounts and carports all use microinverters, while rooftops use string inverters. Microinverters in general allow for a higher power output, which is why we chose them for all the ground and car mounts, and the sheer number of panels on rooftops made us decide to use string inverters in order to minimize cost. Here you can see a snapshot of our Aurora Solar model on Ball State's campus with some of our panels. You can see in the middle is a large parking lot with carport modules, and in the bottom left corner is a building rooftop with only half the roof covered in panels. This goes back to our Irradiance Model decision of only using panels that would receive 85% direct sunlight. As you can see from some of our group members, we decided that this Irradiance model was pretty neat, so we had that as the virtual background. Here is that 85% irradiance setting where you can see the different hot points on the buildings. Areas that have a darker hue, such as the building in the bottom left corner, does not receive any panels because they didn't receive enough sunlight. We used light detection and ranging software, which was invaluable in helping us decide where to place the panels. We needed to make sure that we're not going to place any panels that would be shaded either by trees or nearby buildings. Here is a snapshot of the campus after all the inverters were strung together. Green lines represent parallel connections, while the yellow areas are panels tied in series. You can see on the right building how the panels are connected more clearly. The inverter we chose was the Delta M42U121 with a DC to AC ratio of 1.4. We chose this ratio to minimize clipping during the peak hours of the day while still maximizing power output between modules connected in series and in parallel. At max, this inverter can handle about 12 strings in parallel, but we kept it at 11 to ensure more power output from the individual strings while also reducing the chance of overloading the inverter. The panels on the left side of the screen are connected with microinverters, the Enphase IQ7X, which maximize power output of each cell and can be attached easily to the rear of the panels. Finally, you can see here one of our carports. We designed these in hopes of connecting EV charging stations to promote the future use of electric buses and other university vehicles.
So even though we are all brand new to OpenDSS, we decided to use this software to model our power distribution. In addition to the provided source code, we set a PV line, PV transformer, and a PV definition for our panels with the code. As you can see from this graph, we are creating a more uniformly distributed output and also a higher power output that was previously in place. So in addition to the efficiency of our system, we would also like to talk about the financial implications.
So to finance this system, we recommend that Ball State University sets up a green revolving fund. And this is a fund that's began with a student levy, grants, endowments, or other sources of money. And this fund works by loaning out money to sustainability projects, and this can be done with or without interest, depending on if the fund is looking to grow. And then as these sustainability projects begin to generate cost savings with utilities, they're able to pay that money back into the fund. And so then this money is able to be continually loaned out again and again to sustainability projects. And what's really cool about this fund is it allows projects like this solar project to get upfront capital, and they don't have to take on debt financing at the beginning. So with this fund in mind, we also recommended that Ball State University outright own their solar system. After running our own financial analysis in CREST, and after looking at case studies, we found that for a long-term system like this, outright owning the system is the most financially beneficial. And since Ball State University has already committed previously to sustainability, we think that having this fund would be a good way for them to continually fund these sustainability projects as they move forward towards their commitments. And as you can see in the graphs here on the slide, even if the money from the fund is loaned out with or without interest, the solar project is still able to generate profit. So overall, if the money is loaned out from the fund without interest, our project is able to generate over $5 million in profits. And with an installation upfront cost of about $11 million, and taking into account all the other factors of cost and incentives, we're able to get a 51% return on investment.
So this project occurs in 3 stages. Stage 1 is the construction of the photovoltaic system, which we will detail on the next slide. Stage 2 is community and university education and outreach. So, explaining and using educational materials to explain to the community, to students and faculty and staff, the purpose of the panels and how it relates to the university's mission as a whole, and just addressing any concerns. And then stage 3 will be investment in future research and sustainability projects. So using the money saved to invest in future sustainability projects and in furthering the university's sustainability goals. On the next slide, we can see the construction timeline for the project. Most construction will occur in the summer in order to minimize distractions to student learning and exams and such. And then the next slide, we can see our engagement strategies. So first is participation in the $1 billion Green Challenge to the Sustainable Endowment Institute. So this is a fund that the university can contribute to, and in exchange will receive money for projects or for sustainability projects, and will also receive resources to assist in implementing those projects. Webinars, forums, brochures, workshops, and fact sheets will address common questions such as materials, glare from the panels, economic viability, and any other concerns that anyone from the community or faculty or staff or students may have. And then recent improvements in technology and the improvements in cost effectiveness will definitely be stressed in order to show that solar is a worthwhile investment.
We'd like to thank NREL, the Department of Energy, Aurora Solar, and HeroX, and everyone else involved for the valuable opportunity to learn and grow. We'd like to thank OSU, Solar EO, and the ECE department for their continued support. And we'd like to end our presentation now and open up the platform for questions, comments, and concerns. Thank you again for taking the time to listen to us.